field in physics, mathematics, or other sciences has a very particular meaning, and it's not unrelated to the common understanding we have of field. And I want to stress right in the beginning, starting week 2, this chapter, it's really important that you try and wrap your mind around this general concept of field. Like in mathematics, when you first learned the concept of function, it took you a while knowing many examples and using it to understand in a strong way what function is. So let's start with this term field and start from our common understanding. So our common understanding is an open space, maybe a meadow or a hay field, or it could be a soccer field or a baseball field or a football field, a field that's outlined in a specific way, an open space that's outlined in a specific way for some purpose. But in physics, the meaning is similar but different. It means, in a very general sense, field just refers to any space. So if there's a single word that you would use, if I ask you an essay question, talk about field, just say field refers to space, three-dimensional space. And just like we have soccer fields, football fields, baseball fields, we have electric fields, gravitational fields, temperature fields, wind velocity fields, altitude fields. So in a very general sense, a field is the list or the mapping of all values of some quantities throughout space. Let me pause and write that down. So there it is. Pause the video if you need to read it, think about it. If I ask you to talk about fields in general and specific fields like the electric field that we're going to study now, you should start with this concept and this statement. So the quantities that we might want to know could be scalar quantities or vector quantities. So pause the video and make a list of values that you might want to know throughout space of different quantities and whether they're scalars or vectors. So make a list and then come back and see what I've written. Okay, here are the examples I came up with. You might have some others. Temperature field, that's usually seen as a temperature map, like a map of the United States with all the temperatures. Time field, that would be like the time zones around the world. There's different times in different places in space. Pressure field, that would be another weather map showing the pressure everywhere across some area of space. Density field might be like a map, a cross-section of the Earth, showing the different densities throughout the Earth. And familiar kind of field is a topographic map that has altitude lines that show the different altitudes throughout some area of space. Those are all scalar fields. A wind velocity map, that's another thing you might see on a weather station. The magnitude and the direction of the wind at any point in space, that would be a wind velocity map. Or if we're studying the flow of fluids, like fluids flowing through pipes or water flowing down a river, you could map the magnitude and direction of the water's velocity at any point in space. And then these are three kinds of force fields. The first one we saw briefly last semester, the gravitational field. And this week we're going to learn about the electric field. And weeks maybe 8 or 9, we're going to learn about the magnetic field. And so the two fields that we're most concerned with this semester are vector fields, the electric field and the magnetic field. Okay, here are a wide variety of field examples. So most of you are familiar with topographic maps. Each line represents a height, like 300 feet or 200 feet. And so by drawing these lines and putting the numbers in, it gives you a good visualization of the topography of the area. So mapping out fields, like what it looks like, giving it a good image is important, and that will be important when we come to electric and magnetic fields. How are we going to visualize them? How are we going to picture them? So if we take this map, topographic map, you can see right away, you see like, okay, what are these areas? This is like height is either going up or down because there's no numbers here. But we know that when you reach a point like this or like this, it's either a mountain or a valley. You've reached the highest point or the lowest point. And by putting numbers in here, so it gives you a good visualization of the topography. We talked about density. So here's a density map. If we wanted to be able to visualize the density of the different parts of the Earth, we could use this kind of example. And here we have wind velocities. So this is a vector field. So throughout this area, wherever this is, I don't know where it is, but you can see all the different wind speeds. So you're getting a magnitude of a vector and a direction, right? So as the longer vector is a higher wind speed, and the shorter vector, and it gives you the direction. So this gives you a way to see how the air is flowing through this area, a very good overall picture of the wind velocity field. Another wind velocity field. And here we have some color coding. So the vectors aren't varying in length, but the colors give an indication of the wind velocity. So sometimes you'll see we do that with the electric field. We use color coding to represent different values. And a pressure field represented in colors. So these are the different pressures. You can see the scale on the side. We won't take time to read it, but the high pressures are the reds and the low pressures are the violets and the darker colors. And finally, some temperature fields. Oh no, this is a pressure field. These are in numbers you're not familiar with because we haven't studied pressure, but you can see the different pressure. And to give a good picture, the lines trace out equipressure lines. So like the topographic map, when you see an area like this or an area like this, you know it are a high or low pressure. So you see this is high pressure. This is a low pressure center. And so the lines that connect the numbers of equal values allow us to have a very nice image of the pressure field of the United States at this time. And last but not least, the temperature field. This doesn't have numbers on the map, it's all color coded. Actually, it's kind of hard to read. Anyway, presumably, pretty obviously actually, the darker red and the lighter red, and the yellows lower temperatures, and then the cooler temperatures are in the blue and the violet and magenta. Okay, so now we want to talk about electric fields. Electric fields. So what do we know? You'll see around the periphery a bunch of diagrams. We'll talk about those in a minute. But what we know is if we have two positive charges, they repel each other. And if it's a positive and negative, they attract. But it's puzzling, and it has puzzled people for all time. How does each charge know that the other charge is there? How does this charge, no, there's a charge over here. It's not touching it. It can't see it. It's just like, how does it know? So this puzzled people. So the answer that was proposed, and it ends up being really the answer, is that the first charge, let's take this charge away, that the first charge has an electric field around it. It's not just a charge, it's a charge that's emanating an electric field. Just like a radioactive, what's wrong? Just like a radioactive piece of uranium gives off radiation. Just like a light bulb gives off light. Just like a microphone emits sound. Just like a person emits an aroma that a dog or another person can pick up. So surrounding this charge is this electric field. That's what we mean by the electric field. And so when we bring in a charge, a second charge, it lies in the electric field. So no, it's not in contact, it's not in contact with the charge, but it's in contact with the electric field. So yes, it responds to the electric field because it's in it, it's in contact with it. And so the amount of force now, rather than thinking about, this is a new way of thinking, so listen. Rather than thinking the force on this charge is a result of how big this charge is and how far away it is, that's Coulomb's law. The new way of thinking is the force on this charge depends on how big this charge is and how strong the electric field is. So think of this like wind going out from the fan, right? And as you get further away from the fan, the wind gets weaker. So if I hang a ribbon close to the fan, it's going to blow along a steep angle. If I hang a ribbon far away from the fan, it's going to blow along less an angle. Or if you have a wind velocity detector. So the charge, without this charge, we can't detect the electric field. How do you detect the wind? You hang up a ribbon or a windsock or something. So in order to detect the electric field, we use a test charge. So we're going to call this the original charge. We're going to call this Q1, and the test charge, we could call it QT, but I'm going to call it Q2. This is our test charge. This is the charge that we're going to move around and map out. Just like supposing we wanted to map the temperature field. We'd go around the room or around the country with thermometers and we'd record the temperature and write them down. So that's what we're going to do for the electric field. Watch. Okay, ready? Here's the charge. I took everything out. And now we're going to map out the field. We want a picture of what the electric field is. But in order to detect the field, we need another charge. We need our test charge. So I put the test charge here, and I measure the force. And then I put, you can see that if I put the test charge anywhere else at the same distance, I'm going to get the same magnitude of force, but in a different direction. And if I put the charge so it's twice as far away, the test charge, the force is going to be 1/4, right? Coulomb's law. And so I can drag my test charge around and write down all the vectors, right? If I go to a position where I'm closer by a factor of 2, the force is going to be 4 times bigger. So you can see, you can imagine as I map this out, the vectors are going to be all over the place. And the other problem is, it's going to be hard to make a good picture. That's why we used the field diagram pictures that you're going to see, the field line pictures. But there's another problem. Supposing now you want to map out the field, and you come in to some place, and your test charge is different from my test charge. Let's say your test charge is bigger. At the same distance, you're going to get a bigger force. But we can fix that. Supposing I want to say the electric field at this point is the force that I measured divided by the charge that I used to detect it. In other words, it's the force per unit charge. And so that's going to be, using Coulomb's law, that's going to be K, Q1, Q2 test charge over that distance squared. But when I divide the force by the charge that I use, Q2, the value I get for the field is independent. So when you come over here with your Q2 and it's twice as big, the force you get will be twice as big, but the charge you use is twice as big. And so you end up, even though you have a different test charge, you end up with the same electric field that I measured. And so the electric field then is independent of the charge that you use to measure it. It only depends on the charge that we're measuring the field for. So this equation here, this equation, let me show you. Oops. This equation here is our definition of electric field. By definition, the field is the force per unit charge. And that means the field any place, for 1 charge, for 10 charges, for charged plates, for any charged arrangement, we can measure the electric field simply by putting a test charge at a certain location, like a thermometer at a certain location and measuring the temperature. We push the test charge at a location and we get the electric field at that location, and no matter who measures it with what test charge, you're going to get the same value. Now, if we're talking about point charges, which is usually what we do, is we use Coulomb's law, and so we get this equation. So I'm going to erase all this and come back and just summarize. So let me do that. Okay, so it's important, I'm going to emphasize this again and again, that you understand the difference between these two equations. They are different. This is the definition of electric field. It's the force per unit charge at any point in space. I don't have all this written down, right? But the electric field, if I ask you a question, define electric field, you'll write down this equation, and you'll say the electric field at any point in space is the force per unit charge at that point in space. Okay, that's how we get the value. And so the electric field in any situation will be the same for anyone that measures it, no matter what they use for a test charge. On the other hand, if you have a point charge, only if you have a point charge, the electric field can be calculated by using this equation. So let me give you a couple examples. Let's stay with this since I was just, in other words, if you have a charge, let's take a negative charge in this case. Well, no, let me not bring that up yet. Let's take a positive charge. and I go to this point, I can use the equation to calculate the field. So what is the R? The Q is the charge that we're calculating the field for, and it has to be a point charge. If it's a rod, you can't use this equation. It has to be a point charge. K is K, and what is R? R is always the distance, right? Not between charges, because there is no other charge. R is the distance to the point. So if I choose a different point, the R is going to be different. Call this R1, this R2. This R is going to be different. And the electric field at point 2 is going to be different. And its direction depends on the situation. And its magnitude, if it's twice as far away, is going to be 1/4. So this is the equation you will use throughout the assignment to calculate the electric field whenever you have a point charge. And if you have more than one point charge, let's say we have a positive charge and a negative charge here, and we go to this point, R2, then we'll have an electric field that goes toward the negative charge here, a little bit smaller because it's further away than the positive charge, and you will get the result of the field at this point by adding two vectors, just like you did last week, only in this case there is no charge at the point. You're only calculating the field. That's an important distinction between what we're doing this week and what we did last week. Okay, one other thing that I want to mention here. The other thing is that electric field vectors always point away from a positive charge and and toward a negative charge. And that agrees with the definition because the electric field is a vector. If the charge is positive, the direction is in the direction of the force. If the test charge were negative, the direction of the force would be, the direction of the field, because this is negative, would be opposite the force. So notice, if my test charge in this case is a positive test charge, the force will point this way and the field is that way. If instead I use a negative test charge, the force would be this way, but the field would be opposite the force because the Q would be negative. So anyway, the important thing is to remember that the electric field always goes away from a positive charge and always goes toward a negative charge. That's important to remember. That will come up again and again in the assignment. So, oh yes, there is one more thing. Let me pause the video. Okay, just to summarize. This is our definition of electric field. If we have a point charge, more than one, we can calculate the electric field at any point in space. Remember, it's a point in space, not on the charge. That'll be important when you do the assignment. Any point in space, we can use this equation, and we use it one time for every charge. So if there were 3 charges and we go to some point and we're calculating the field, there are going to be 3 electric field vectors that we have to add. So that when you do the assignment, this will become clear. Okay, the last thing is, how do we picture or represent these fields? They're maps, right? And we looked at temperature maps and pressure maps. It's important to have a good way to map and visualize the electric field. So one way we might do that, and we do use this way, is to take a charge and show the field by vectors. So this is a vector representation. And notice the detail. The vectors close to the charge are bigger, and then they get smaller and smaller as they go away. But these vectors are not really to scale. If you look at this vector here, it's probably 10 times further away than this vector. So it should be 100 times smaller. So using vectors to represent the field is not a very good way because you can't do it well. And you'll see in some of the lab problems where they use vectors, they color code the vectors just like we saw with the temperature and pressure maps. But there's a better way and a more widely used way to picture electric fields, and that way is to use field lines. So here's the alternative to the thing that I just showed you. And when we use field lines, there are a list of rules that we use to interpret and understand field lines. Some of them are intuitive and some of them are not. So now I'm going to write down the rules for interpreting electric field lines, and these are the rules that you should learn and even memorize because they'll come up in the assignment and the quiz next Monday. Okay, here they are. The 5 statements or rules of electric field lines. You want to use these, you want to memorize them, and let me just mention that you can find these in the class notes. In fact, I should mention, take a look at the class notes, and these were on page 5. They're an old set of notes, but there's a lot of useful information in there related to fields and electric fields. So take a look at the notes as well. So here they are. The first one is electric field lines always start on a positive charge and end on a negative charge. So if you see a field line starting or ending in space, it's only that you just don't keep drawing it. A field line never really truly ends until it gets to a negative charge. And a field line can't start out of nowhere. It has to start on a positive charge. This is something that's very important. Again and again, you'll see it come up. The number of lines have to be proportional to the charge. So if you have 8 lines coming out of one charge and a second charge is twice as big, you need to have 16 lines. And you'll see this as we look at diagrams in the future. The density of the lines are an indication of the strength of the magnetic field. So I often picture this like a light bulb, right? You have a little tiny light bulb with rays of light going out. And if you have a light meter that measures the intensity of the light, it gets weaker the further you get away from the light. This is a 1 over r squared. We've talked about this, 1 over r squared dependence. And so the field in picture gets weaker as the lines spread out. The direction of the electric field for curved line, for any curved line, like if an object is traveling along a curved path, its direction is always tangent to the curve at that point. So the direction of the field is always tangent to the curve. I'll show you this in a minute. And lines can never cross, because if 2 lines cross, that means there would be 2 different directions to the electric field, which is impossible. So when you have a unique direction, you'll see in a correct diagram, field lines will never cross. If you see them crossing, there's something wrong with the field diagram. So these are the rules that you need to learn. Let's apply them to a few of the situations we have here, and then I'll close this video, and the applications using all this to solve problems, I'll either make a second video or you will do as you do the assignment. Okay, so here we see the field lines going out, and remember, they're not ending here, they just keep going, but we stop drawing them. They're originating on a positive charge, and if you count the number of field lines, that will be proportional to the charge. If this has the same number of field lines, automatically you know that the magnitude of the charge is the same. And again, these lines aren't starting here, it's just that we can't draw them all the way off the page. Field lines only end or start on positive and negative charges. And if those are two independent charges, that's why the line is there. But if we take a positive and negative charge and actually put them in the same space together, not in different places, then the field looks like this. And so what that means is you can see as the field lines spread out, the field is getting weaker. You can see field lines originate on a positive charge and end on a negative charge. And these field lines actually go up here and connect. Go like that. This field line would go way up here and connect to that one. This field line would go way off the page and come back here. So all these field lines, we're just not showing them, but they all start on the positive charge and end on the negative charge. And the density of line indicates the field strength and the direction. So if we go up here, the direction of the electric field is in this direction. And you'll see that if we pick this point and we want to calculate the value of the electric field here, we would have two vectors, one going in this direction for the positive charge, a second vector going toward the negative charge from this point. And when you added those two vectors, there were problems in the assignment like this. When you add those two vectors, you end up with a single vector in this direction. And so the electric field is always tangent to the line, and you see that none of the lines cross. Okay, there's four situations that you should be familiar with. The point charges by themselves, the 2 point charges together, a dipole, that's a dipole field. You should know what that looks like. That comes up a lot in the assignment. And the other one is a line of charge. So if we have a charge rod, then the field looks like this. And this will come up in the assignment as well. And so you should know when you're looking at the rod along the axis, the field lines, except when you're near the edges, point straight up. But if you rotate the rod 90 degrees so it's facing you, it'll look like a point charge. And the field due to a rod looking down the axis of the rod will be just like a point charge. So it's good to be able to visualize what the field due to a charged rod looks like. And the final one is two plates. Well, let's look at this actually. This is useful, another useful example. So here's our electric dipole. We don't call this a dipole, but it's two charges that are the same, and you see the field lines even here don't cross, and you can see there's an area here where the field is 0. You'll actually calculate that in the assignment problem. Supposing you're reading a point charge and a plate, then the field lines are going to go over, and near the plate, the field lines aren't spreading out, they're uniform. So that means that the field here is uniform, and if we bring two oppositely charged plates together, the field lines will go from one plate to the other. And you see they're not spreading out. So the field in this region is uniform. It doesn't vary. And so that means that if a charge enters this field, it will be subject to a force which is constant, and constant in magnitude and direction. And so a charge entering this field is going to behave like a projectile. If it's a positive charge, it's going to bend down in a parabolic path. That's going to come up in a lot of the assignment problems as well. So we have point charge fields, dipole fields and charged rod fields, and the field between two charge plates, a uniform electric field. Those field arrangements are ones that you want to become more and more familiar with over the course of this week and for the rest of the course. Okay, went a lot longer than I expected, but that's it. That's the introduction to electric fields.